Welcome everyone to our second of two videos on the mole concept. In our first video, we looked at Avogadro's hypothesis and the development of a relative atomic scale. In this video, we are going to look at why we needed this concept that we refer to as the mole, why it was developed, and then we're going to clearly define what a mole is in the context of chemistry. Let's just remind ourselves what we were looking at last video. So in the previous video, we showed that the development of a relative atomic scale allowed for precise chemical reactions to occur. If we think way back to the start of the last video, we saw that the whole point of this exercise was to develop chemistry into a quantifiable science. The challenge with chemistry, of course, is that what we're trying to measure is too small to measure directly. So we got around that with a relative scale. However, that really wasn't good enough for chemists, in that a whole group of chemists still wanted to develop a precise mass for an atom. By precise mass here, I mean a mass on an absolute scale, not that hydrogen is 1/16 of the mass of oxygen, but what is the mass of a hydrogen atom in grams, so an absolute scale. The reason why this is important, and the connection to that relative scale, is that if chemists could manage to measure atomic mass for one single element, then, because a relative scale had already been developed, the mass of every other element can be calculated. For example, if the mass of a single hydrogen atom could be measured in so many grams, well, the relative scale tells us that oxygen is 16 times heavier than hydrogen. So rather than having to go again and experimentally measure the mass of oxygen, you could just do it through calculation. You could say, well, here's the mass in grams of hydrogen. Let's multiply it by 16, and then we get the mass of oxygen. So the relative scale is still valuable and is still going to be used, and is still used to this day, as we'll see. So determining the mass of a very small particle, an atom, was the first challenge. Now, we are not going to get into detail about how chemists solved that problem. There's a series of really ingenious experiments over the course of many years, which arrived at a very precise mass of several different elements. But that's not something we're going to focus on. So let's just leave it to say that over the course of many years, this was found that the mass of a single element could be measured. The mole concept is more closely connected with the second problem, and that is this. This number here. Let's count the zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So why do I have this number here? Well, this is approximately, or at least in the range, of the number of atoms and molecules that are involved in small-scale chemical reactions that we would do in a high school chemistry laboratory. This many. So every time you're carrying out a reaction, even if it's just in a very small beaker, you're reacting about this number of atoms and molecules. There's probably a name for this specific number, but it'd be a really big pain to be talking about this amount of atoms or molecules all the time, having to write out all those zeros when we're talking about the number of atoms and molecules which are reacting. So the second problem that chemists have is that the quantity, the sheer number of atoms and molecules which are involved in even very small reactions is astronomical. So we're dealing with huge quantities of very, very small things. So what chemists developed was a way to simplify the way we talk about huge quantities of particles. I like to summarize this problem as the problem from going to microscopic to macroscopic and macroscopic to microscopic. The idea is that chemistry is happening on the atomic level, okay, submicroscopic, but I'll use the term microscopic. You'll get the idea. Chemistry is happening between atoms and molecules, small whole number ratios. But we can only experience chemistry on the macroscopic level. So, as I said in a previous slide, chemists developed a way to measure the mass of a single atom. That's great, incredible scientific achievement. But what's the use? When we're carrying out chemistry, even on a small scale, we're reacting huge quantities of atoms. And on a practical level, there's no direct way to weigh those individual carbon atoms. Okay, you can't get a scale that measures to a level of precision down to 10 to the negative 23 grams. It's impossible. The challenge for chemists is we need a way to go from the atomic level to the everyday experience level that we deal with in terms of regular chemistry. And this is where the mole concept is coming in. Chemists want to be able to describe precisely the quantity of chemicals which are reacting. But it's a real pain to talk about that in terms of grams because atoms are so small. It's also a pain to talk about such huge quantities of things because there are so many atoms and molecules reacting. So another way to rephrase the problem is that chemists need a way of talking about large quantity of things in an easier way. Well, we do this all the time. We do this by inventing a new word that groups things together in a standard way. The best example of that is the word dozen. Groups of 12 things, eggs, bagels, donuts, are often grouped in groups of 12. And then rather than talking about the number of bagels, the number of donuts, the number of eggs as 12 eggs, 24 eggs, 36 eggs, we talk about them in terms of the number of dozen. I'd like 2 dozen eggs. And this word dozen groups things together in a standardized way so that when someone says a dozen to you, you know that they actually mean 12. So this is an everyday example of the way we use a grouping word to make things a little bit easier in the way we talk about items. The mole is the chemist's dozen. What do I mean by that? Well, a mole in chemistry just refers to a number of things. Now, a lot more things than a dozen. Specifically, 1 mole is 6.02 times 10 to the 23 things. Now, we'll get more precise about what I mean by things, but just think of the mole as a word that means a specific number of things. A dozen always means 12. A mole always means 6.02 times 10 to the 23. Why this number? Well, there are 2 reasons. First, let's talk about the scale. What do I mean by that? Well, I mean the last part of that number, 10 to the 23. Remember that really huge number I put up on the screen? That was to the 10 to the 24. So the scale of this number, 10 to the power of 23, is on the scale of the quantities of atoms and molecules that are reacting or involved in everyday quote-unquote samples. So that's the scale of the number. We're using a term that refers to a huge number of things, and specifically the number of things that we experience on the macroscopic level. The second part of the number is that specific value, 6.02. The specific numerical value, 6.02 times 10 to the 23, was chosen to create a simple conversion factor between the mass of a single atom and the mass of a huge quantity of atoms. So let's get some more specifics. The mole is actually a standard unit, okay? It's one of the base SI units, like kilogram, like second. And so just like the measurement of seconds has a symbol, S, the mole has a symbol as well. And they didn't really do much to it, probably because all of the other symbols were taken. But the symbol for a mole is just MOL, okay? You may ask, what's the point? It's a good question. That numerical value that I introduced on the previous screen is a constant. And it's named after Avogadro, who really started all of this with his hypothesis. So N sub A, so N with a subscript of A, is referred to as Avogadro's number, and it's a constant, 6.02 times 10 to the 23. What that means is when we use the term mole, it's always referring to this specific number of things, whether we're talking about grains of sand, atoms, molecules, stars, whatever you want to be talking about. If you talk about a mole of something, that is referring to 6.02 times 10 to the 23 things. Another way of saying that is expressing it as a ratio. So I use the term things. In the precise definition of the mole, they use the term entities, okay? It means the same thing. N sub A is equal to 6.02 times 10 to the 23 entities per mole. That's just another way of saying is 1 mole contains 6.02 times 10 to the 23 individual entities. Leading into our next video, which is going to be on relating mass to moles, here's a question for you to answer. I said on a previous screen that the mass of a single carbon atom has actually been calculated. And it's specifically equal to 1.993 times 10 to the negative 23 grams. That's the mass of one carbon atom. If that's the mass of one carbon atom, what is the mass of 1 mole of carbon atoms? Remembering that 1 mole is equal to 6.02 times 10 to the 23 atoms. See if you can figure that out. It'll be good practice in relating the idea of moles, and also be good practice using scientific notation, because we'll be needing that a lot over the next couple of lessons.